Okay, maybe it's time we can get started soon. So welcome to the Spring 24 Winston Co-Lecture. I'm David Brett. I hold the Winston Co-Chair, but my main role here is to introduce the Dean of Letters and Sciences, Estella Actiquana, to give the real introduction.
All right, thank you so much, Dave. And I just want to say welcome to all of you this evening for joining us for the Winston Co-Professorship in Science Leadership Lecture. Before we begin, I'd like to take a moment to welcome the Co family, Katie and Hal. I'm so impressed that every year they come here to come and listen to the great minds that we invite to come here. So we're really, really appreciative, especially for you coming all the way from San Francisco this evening to be here. We really appreciate that. So Katie, without you and your late husband, Professor Emeritus Winston Coe, this remarkable series wouldn't be possible. Your unwavering dedication to our community has made an indelible impact. So thank you so much. So Winston Coe was more than a physicist. He was a visionary leader who dedicated 41 years of his personal life to UC Davis, serving as chair of the Department of Physics, and then later on as dean of the Division of Mathematical and Physical Sciences. His passion for science and education left an enduring legacy that continues to inspire all of us today. Winston and Katie's generous endowment established the Winston Coe Chair in Science Leadership and the Winston Coe Public Lecture Series. These initiatives have brought some of the brightest minds to our community, fostering an environment of learning and innovation. And today we are honored that we have amongst us distinguished Professor Dave Britt, the inaugural co-chair, whose groundbreaking research on harnessing solar energy to produce hydrogen holds the promise of revolutionizing our approach to sustainable energy. Thank you, Dave, for embodying Winston's spirit of excellence. The first co-public lecture actually took place about 8 years ago in 2016, when physics professor Veronica Hobney took a rapt audience on deep dive into the nature of black holes. Since then, we've welcomed luminaries like chemist Daniel Nocera, a pioneer in renewable energy, and biochemist Squire J. Booker, who is at the forefront of combining antibiotics resistance. Each speaker has really enriched our understanding and ignited our curiosity. This year's speaker, Professor Kenneth Ribet, joins this esteemed group. Professor Ribet is a professor emeritus in physics from UC Berkeley. Professor Ribet's expertise in algebraic number theory and algebraic geometry has made profound contributions to the field. And his talk today, Fibonacci, Congruent Numbers and Elliptic Curves, promises to be a fascinating journey through time and mathematics from the 13th century insights of Leonardo Fibonacci to contemporary conjectures that continue to challenge and inspire us. Professor Ribet received his PhD from Harvard University and taught at Princeton before joining UC Berkeley in 1978. He has served as president of the American Mathematical Society and is an elected member of the American Academy of Arts and Sciences, as well as the U.S. National Academy of Sciences. Professor Ribet was inducted as a, let me see if I can get this French right, I'm supposed to be able to know him coming from Cameroon, Vigneron d'honneur by the Jurats de Saint-Emilion in 1988. He was awarded the Fermat Prize in 1989 and the Brouwer Medal from the Royal Dutch Mathematical Society in 2017. So without further ado or delay, please help me in welcoming Professor Kenneth Ribet. We are so eager to hear your insights and be inspired by your journey through the world of mathematics. So welcome.
Okay, thank you very much for that great introduction. It's an honor for me to have been invited. It's a pleasure for me to be here. I am a number theorist. That's the kind of mathematics that I do. So you will be seeing a lot of numbers and also some equations, but always the same equation over and over again. So I'll explain what that is when it comes up. So there are three topics. Fibonacci was a person from the 12th or 13th century. Congruent numbers are things that I will explain, and elliptic curves are a very old tool in mathematics that has been incredibly useful in all different parts of mathematics and well beyond mathematics in the different sciences. And the point is somehow to explain how these elliptic curves are helpful in thinking about these numbers that are called congruent numbers. So I'm really going to start with the last thing, elliptic curves. So elliptic curves are given by an equation, y squared equals x cubed plus a cubic. And the point is that these numbers that you take to be capital A and capital B can be very simple numbers like -1 and +1. So here on the left, you see a graph of an equation of this type. And the point is that when x is very small, like it's say -2 or less, then on the left side of the screen, there's kind of nothing, because you're trying to take the square root. Y is the square root of x cubed minus x minus 1, so there won't be any possible y's. But if you sidle up to -1, there's a specific value of x, some irrational value, it's not a fraction, where x cubed minus x plus 1 happens to be 0, and then y can be on the curve, it'll be 0. But then if, for example, you take x to be -1, then x cubed minus x is 0, so x cubed minus x plus 1 is 1, and y can be +1 or -1, either of the square roots of 1. And a little bit more racing toward the right-hand side, if you take x to be 3, 27 minus 3 plus 1 is 25, so y can be plus or minus 5. And as you go to the right of 3, there will be some y's, but they kind of go off the screen, so they're not depicted in this particular slide. And the point is that for most values of x, like if you take x to be 3.14 or something, you'll get some y, but that's probably not interesting in number theory unless you really take 3.14, which is 314 divided by 100. But if you take the number pi, then that's not a number that number theorists worry about too much in this context. The idea is that you want to pick out those solutions that are whole numbers. The technical word for a whole number is an integer, and also those solutions that are fractions, like 3/4, and the technical name for a fraction is rational number, rational as in ratio. And so the interest in the subject of elliptic curves, well, I did say elliptic curves are useful for all sorts of different things. So there's lots of interest in lots of directions. But one thing you can do with an elliptic curve is ask whether or not you can gain some insight into the points on the curve that have fractional coordinates. So for example, 1 comma -1 is such a point, or 1 comma 1, that's in this example the gold point. The points are blue or gold because the UC Berkeley sports teams, or the colors of Berkeley are blue and gold. And Davis too, okay. Now, the personage that I want to bring up here is Diophantus of Alexandria, who seems to be a real person, unlike, say, Pythagoras, who may not have actually existed. He might be some construct of early history. And Diophantus was interested in the kinds of questions that I just alluded to, where you would give one or several equations and you try to find out the solutions to those equations that had whole number or fractional values. And he wrote a treatise called Arithmetica, which apparently is thought of as consisting of 13 books. I never knew that until I was preparing to come speak to you. I always thought of Diophantus's Arithmetica as a single book. It may be that the books were more like chapters and they were put together. And as you'll see in a moment, Pierre de Fermat, 17th century mathematician, was very fond of Diophantus's work. Diophantus was the very beginning of European number theory. People tried to understand Diophantus's techniques and generalize them in different directions. And in honor of Diophantus, we talk about Diophantine equations. So that's an entire subject in number theory where the aim is to solve these equations in specialized numbers. And it turns out that elliptic curves have been in the forefront of mathematical research because we haven't yet figured out everything that we want to know about elliptic curves, despite the fact that they have been researched literally since the early Greek mathematicians. And to put two things in contrast, you can take two elliptic curves, that's what they're called, where the coefficients A and B are 1 and 2, and in the first one, it's 1 followed by 2, and in the second one, it's 2 followed by 1. So these are kind of sibling equations. And the first equation has only two solutions in fractions. They happen to be ordinary integers, -1, 0, and 1 plus or minus 2. If you take x to be 1, then x cubed plus x plus 1 is plus 2 is 4, so y is plus or minus 2. But on the other hand, if you just change things a tiny bit and you have 2 and 1 instead of 1 and 2 as the coefficients, then there are infinitely many rational solutions, as was the case, by the way, with the blue and gold points on the previous slide. There are infinitely many rational solutions, and you can try to list them. They get more and more complicated in the sense that the denominators grow very rapidly, but you can't list them all because there's an infinite number. But what's interesting is that if you want to use a laptop to study elliptic curves, you load the appropriate software package, and the package will tell you very quickly, literally in milliseconds, whether or not a cubic equation has infinitely many or finitely many solutions. But one of the embarrassments in modern mathematics is, despite the fact that we've trained all of our techniques on this problem, we don't have an algorithm in the sense of computer science that is guaranteed to terminate in some bounded amount of time, given the inputs, that will tell you whether or not there's an infinite or a finite number of solutions. And so this is an example of an algorithm that works fine in practice, but is not known to work in theory. And it's kind of the, those of you who've been to Berkeley, you might have visited the Simons Institute for the Theory of Computing, and that's one of their slogans on their t-shirts. It works in practice, but does it work in theory? And this is a kind of poster example of something where we don't know the answer. I've said that elliptic curves are used all over the place. They are unreasonably effective, and I think that was the phrase of Freeman Dyson. And they really came into the public eye in 1993 when Andrew Wiles announced that he had put together a proof of Fermat's last theorem. So on June 24th, 1993, this was the front page of the New York Times with an article by Gina Colada. And I'm actually mentioned, there I am, you might see my name in the center of the screen. I'm actually mentioned in there, and there's an embarrassment because Andrew Wiles told Gina Colada, well, I'll let Ken speak for me. And I kind of told her how great the proof was and how great Andrew Wiles was, but the article refers to me as his spokesman. And so I got, for months and practically years, I got phone calls from all sorts of people, you know, so I was his press secretary. But one of the results is that I got invited to give lots of lectures on Fermat's last theorem. And I came in particular to Davis soon after there was a program on NOVA about Fermat's last theorem in which we all appeared. I was invited by the physics department, And in preparing to speak to you, I found that I had copies of the email with Professor Chow, Ling-Li Chow, who invited me. And I'm pretty sure that Winston Coe was among the people that I met, but it was 1997, so I don't remember specifically. But now that I've given you some equations, I'll kind of go back to more simple things, which is Fibonacci. So Fibonacci is known to most people for what are called the Fibonacci numbers, or the Fibonacci sequence. So when I was a kid, I learned the numbers were 1, 1, 2, 3, 5, 8, and the rule is every number is the sum of the previous two numbers, and then the computer scientists got in and they prepended 0. So the 0th Fibonacci number is 0, and the first Fibonacci number is 1, and the third Fibonacci number is 2, and the fifth is 5, and so on. And Fibonacci, to most people, is known for these numbers, and there's even some story about how he was trying to calculate the number of rabbits that would be produced if you started with 2 rabbits over time. And these rabbits were produced rabbits as well as they could. And the thing is just part of popular culture. So here are the Fibonacci numbers on the back of a car that I see regularly in North Berkeley. This is the North Berkeley Fibonacci leaf, clearly from somebody who is very fond of the Fibonacci numbers. And I did just teach a course. We have semesters, so my last lectures were at the end of April, and the final exam was May 7th. I did a discrete mathematics course in Berkeley, and a lot of the material is related to the Fibonacci numbers. But there's more to Fibonacci, which is that he wrote a book called The Book of Squares that I really didn't know about until relatively recently. And I tried to find out what I could about Fibonacci. It turns out he was born at the end of the 12th century, which was a really long time ago. You know, like you could watch, Monty Python and the Holy Grail, and I think that was the 12th century. And he was not known as Fibonacci. I think the fib is fils. He was the son of someone named Bonacci, and he called himself Leonardo the Traveler from Pisa. And in the 19th century, someone decided to call him Fibonacci. They gave him this nickname, and it has stuck ever since, for almost 200 years. But there is this book of squares that was published in the early 13th century, 1225. And what are the squares? The squares are just the numbers that you get by squaring the positive integers. So 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and 7 squared. These are numbers that we know, 4, 9, 16, 25. It seems surprising to write a book about the squares, but this was the very beginning of European number theory. It was written at a time when there wasn't modern algebraic notation. And so if you wanted to write, x squared plus y squared equals z squared, you had to have some circumlocution. Well, and the first number when squared added to the second number when squared is equal to the third number when squared. Well, this is okay at the beginning, but if you have some proof involving auxiliary quantities, then it becomes very difficult to parse. And the translation and parsing was done by someone named Sigler, who also explains after each chapter what actually went on in the chapter after you in modern notation. And the 13th century, I asked Google, really probably artificial intelligence, what was life like in the 13th century? And the answer was it was harsh, and women were subordinate to men. This is really the old times. And children had a 50% survival rate beyond age 1 and started to work around age 12. But here are the squares at the same time. Fibonacci was interested in them, and he had a number of what we call theorems about squares. And one of the things that really interested him was the possibility that you could have 3 different squares that were in an arithmetic progression. So what's an arithmetic progression? It's 3 or more numbers where the differences are constant. Like if I have 1 and 4, and I want to have an arithmetic progression, 4 minus 1 is 3, so the next term will be 7. Now, only 1 and 4 are squares, 7 is not, but you could be a little bit more clever, and you could have 1, 25, and 49, where the differences are equal. They're both equal to 24. And Fibonacci zeroed in on sequences like that, 3 different squares, and he thought about these sequences in different ways. Of course, one thing to do is to say that the middle number is the average of the first and the third. So if you add 149, you get 50, which is twice 25. So that's just a perfectly good algebraic way of doing that. The other way to say it is the way that I wrote, where the differences are equal to each other, and they're 24. And with modern technology, we can write down lots of sequences like that. I have a sequence where the differences are 720, and a sequence where the differences are 100,800. You can do lots more. And the one way you can do this is you can find a formula that actually generates them. But what I wanted to point out is that if you have a sequence like that, you take the common difference, 24, 720, 100,800, and you give it a name. You call them a congruum, congrua, that's the plural. One of them is a congruum in Fermat, in Fibonacci. He wrote in Latin. And today we refer to these numbers as congruent numbers. And there's a little bit of sleight of hand that's about to come in, where we take these numbers and we make them smaller by stripping out any square factors that they happen to have. So for example, 24 is 4 times 6, and 4 is a square, so we just kind of get rid of it, and we say that not only is 24 a congruent number, but we also say that 6 is a congruent number. And if you look at these 720, it's going to be highly divisible by some things. You can pull out stuff pretty quickly, as you'll see on the next slide. And so you kind of get rid of all the fat and just get to the essential square-free part of these numbers. And the numbers that you get are actually remarkably small in these cases. So I already did 24, which is 6 times 4. 720 is 144 times 5, 144 being 12 squared. So 5 is a congruent number, as is 6. And when you get rid of the fat in 100,800, you're left only with 7. So this is the sleight of hand. We kind of say, well, we'll just get rid of these squares and therefore just focus on what's left. When you do that, and what you get are the simple numbers 5, 6, and 7. And this is kind of the opposite of adding squares. You see, because if you have a progression a squared, b squared, c squared, like 1, 40, 25, and 49, you can take this progression and you can multiply by t squared by taking each of a, b, and c and multiplying them by some number t, whatever t you like 100,000. And so you can inflate congrua and make them bigger, and it seems only just that we can deflate them and make them smaller by taking out square factors. And when we do that, we see that 5, 6, and 7 are congruent numbers. Now, when you do that, you get some, I'm just putting in front of you something I've already said. Getting rid of the square factors of the 3 numbers leaves you with 5, 6, and 7, and we will agree, I hope, to call these congruent numbers. And then the question is, basically, the broad question is, what actually are the congruent numbers? And to make the problem kind of focused, what we'll do is just take the numbers that are not divisible by any squares, so we make them as simple as possible. And this is actually the problem that I think is central to what I want to describe. And we can look at the small square-free numbers, which are 1, 2, 3, not 4, because 4 is a square, 5, 6, and 7, not 8, because 8 is 2 times the square, and not 9, because 9 is already a square. So if you just go from 1 to 9, 6 of the numbers are square-free. And you can ask, what about 1, 2, or 3? Are they congruent numbers? And then we get to the 17th century, and Fermat, whom I already mentioned, stood up and proved in his writing that 1, 2, and 3 are not congruent numbers. And the question is, how did he do that? Well, he had a technique. He had a kind of crank that he would use every time he wanted to prove something. If he wanted to prove that some equation didn't have a solution, what he would do would be to suppose that there was some solution, and then he'd say, well, among all the solutions, take the smallest one. And then his technique was to manipulate the solution using elementary properties of whole numbers until finally, at the end of his proof, he got an even smaller solution. And he said, well, this is impossible because I chose the smallest one, therefore there must be something wrong. The thing that I reject is my assumption that there was a solution at all. And this idea of taking something and making it smaller was called his method of descent. That was kind of his favorite method. And as I already said, his favorite book at the time was the book by Diophantus on number theory. In fact, you may know that Fermat's last theorem was called Fermat's last theorem because Fermat wrote in his copy of Diophantus in a marginal note that he could prove the theorem, which is that the sum of two nth powers was never again an nth power for n bigger than 2. And the remarkable thing is that Fermat's copy of Diophantus, which was annotated and republished by his son, Samuel de Fermat, actually is lost. So no one knows what happened to Fermat's favorite copy of this book, in which he wrote all of his marginal notes. And I do want to make a tiny digression, which is that when people talk about Fermat's last theorem, very often they talk about the Pythagorean theorem of high school. So in high school, we take a right triangle with sides A, B, and C, and we prove the formula that a squared plus b squared is c squared. And then it's very natural to ask, is it possible for a, b, and c all to be integers? And this question was studied extensively by the ancient Greeks. They knew the answer fully. They could really dominate quadratic equations, things with exponent 2, and were quite deflated by the fact that they couldn't do cubic equations, which is what elliptic curves are really about. But they knew everything about quadratic equations, and they could write down Pythagorean triples, as they're called, like 3, 4, 5, and 5, 12, and 13. And it turns out that when you do a tiny bit of algebraic substitution, you can get from 3, 4, 5 to 1, 5, 7, which are the numbers that you square in Fibonacci's first example. And the way you do that is you take the difference between 3 and 4, that's the 1. You take the sum of 3 and 4, that's the 7. And the 5 that's being squared on the right-hand side is the middle number 5 that you square to get the arithmetic progression. And so the arithmetic progressions that you study to make congrua are really closely related to Pythagorean triples, and it's because the Greeks told us all Pythagorean triples that we really know how to generate very quickly all the 3-term arithmetic progressions of squares, which are the things that Fibonacci was studying. So I do want to keep that short. This is really a digression, but if you look at a Wikipedia page for congruent numbers, which are the numbers that I'm talking about, you'll find out that a number is a congruent number if and only if it is the area of a right triangle. So the area here is AB divided by 2, but when you take right triangles and you take their areas and hope they're these congruent numbers, the sides of the right triangle are allowed to be fractions and not just integers. So as an example, a very simple example, if I took the 3, 4, 5 triangle, because 3 times 4 is 12, the area is 6. And that shows you right away that 6 is a congruent number from this other perspective. But if you want to display a triangle whose area is 5 or a triangle whose area is 7, then you really do need fractions in order to produce the area. And it's quite remarkable, these numbers are also in Wikipedia, that if you want to make a triangle with area 7, you have to have 24 over 5, 35 over 12. You multiply them together and you'll get 14, divide by 2 to get the area, and you'll get 7. But the thing you have to check is that the square of 24 over 5 plus the square of 35 over 12 is the square of 337 over 60. When you see that and you do the calculation, you'll say, wow, that's pretty amazing. And that's the other perspective on this congruent number problem. But if you want to find out very quickly, for your own edification, which numbers, say from 1 to 1,000 or whatever, are congruent numbers, you can look at an online resource which is called the Online Encyclopedia of Integer Sequences. And this is, the URL for it is oeis.org. And I did that. I found the square-free congruent numbers up to a pretty large value from OEIS. And here's the very beginning of the sequence. You don't see 1, 2, or 3 because Fermat proved that they're not congruent numbers. You don't see 4 or 8 because they're not square-free, and they're also not congruent numbers, as it turns out. But you do see 5, 6, and 7, 13, 14, 15, and so on. And I stopped at 119 only to get these numbers to fit on the slide. But you can get lots of information from the online resource. And as a little bit of eye candy at the bottom, it turns out that there was some big anniversary of the Online Encyclopedia of Integer Sequences just about a year ago. And in May 2023, there was an article in the New York Times, which you can find very quickly by doing a Google search for what number comes next, New York Times, and that will get you to this article. But when you look at these numbers, it depends how embedded you want to be in patterns. You'll see that there are a lot of runs of 3, like 5, 6, and 7 is a run of 3. 13, 14, and 15 is a run of 3. 21, 22, and 23 is a run of 3. That shows you that something might be going on. One of the first books that were published about mathematics after the proof of Fermat's last theorem was a book by Keith Devlin called Mathematics, the Science of Patterns. And when that came out, I kind of asked myself, you know, is that what mathematics is? Does that cover everything that we do? It came pretty close. Mathematicians are looking for connections and patterns. It was a good hook to get people reading to publish this book, which did devote some time to some real estate to Fermat's last theorem, but also to other problems that interested him as he was writing. And nowadays, if you want to look for patterns, one thing that you could do is you could feed your data to ChatGPT. So this is really something that no one would have thought to do 3 years ago. But artificial intelligence, as for many, many things, is getting so good that you're actually able to find mathematical relations by asking AI to search for them. And there's this general feeling that people are going to start finding things that eluded them just by, letting the search engine, large language model, deal with the numbers. And what ChatGPT would tell you is that these runs of 3 occur when you look at the numbers modulo 8. So what does that mean, modulo 8? It means you take the number, like say 79, and you divide by 8. If you take 79 and you divide by 8, it's close to a multiple of 8, namely 72, but then it is 7 more than that multiple. And the remainder on division is called the number mod 8. So you look at the remainders of all of these numbers, like for example, 23 has remainder 7 when you divide by 8, because 24 is a multiple of 8. And when you divide a number by 8, the remainders could be 0, 1, 2, 3, up to 7. There's 8 possible remainders. But if the number is square free, it's not going to be divisible by 8, and it's not going to be divisible by 4. So there are only 6 possible remainders, 1, 2, 3, or 5, 6, 7. And what you'll see is that the remainders 5, 6, or 7 give rise to the number being a congruent number. It kind of tells you that that's happening. And the remainder 1, 2, and 3 tells you that the number is very unlikely to be a congruent number. For example, 1, 2, 3 themselves are not congruent numbers, but also 9, 10, and 11 are not congruent numbers. And 17, 18, 19 are missing from this table. But if you go along the table, on this small compact table, you'll actually see 3 numbers that are different from the others. Those are the ones in red. And they do have a remainder that's either 1, 2, or 3. So, for example, 32 is a multiple of 8, so 34 has remainder 2. When you divide by 8, it's what you call 2 mod 8. And 41, what is that? Well, 42 is, wait a minute, I'm blanking out. 40 is a multiple of 8, so 41 has remainder 1. And 65 has remainder 1 as well, because 64 is a multiple of 8. And so you have something that is not as neat as you would like, namely, you suspect from the table that all the numbers congruent to 5, 6, and 7 are congruent numbers, and the table suggests at first that the numbers congruent to 1, 2, or 3 are not congruent numbers, but sometimes they are. And the question is, can you explain this by using the appropriate kind of mathematics? And obviously, I'm here, the answer has got to be yes, right? Otherwise, I wouldn't be explaining things in front of you. And it's also going to have to do with elliptic curves, because I spent some time talking about these cubic curves. But the real answer is that in order to explain what's going on, we have to invoke some unproved conjectures about elliptic curves. And these conjectures are actually among, mathematicians would say, among the most central conjectures that remain to be resolved. In fact, in the year 2000, the Clay Mathematics Institute had a very short list of millennial problems. And the conjecture that I want to discuss was one of those millennial problems. So how can I bring in elliptic curves? Well, the simple answer is that elliptic curves have been known to be connected to congruent numbers for a very long time. And the reason is just simple algebra. So what you do is, you take an elliptic curve as y squared equals x cubed plus ax plus b. Well, you're asking whether n is a congruent number. You take a to be minus n squared and b to be 0. That's pretty simple. And you can ask for solutions to this cubic equation. Well, if x is 0, y is going to be 0. And also, if x is plus n or minus n, you'll see that x cubed minus n squared is 0. So y, again, is going to be 0. And the question is, are there solutions with y non-zero? And the observation, which is really just high school algebra, is that there are solutions with y non-zero if and only if n is a congruent number. And on this slide, I explained half of the algebra, namely if x cubed minus n squared x is a non-zero square, and here we're just talking about fractions, rational numbers, then you can write down 3 squares of fractions where the common difference is going to be n times a square. And you strip away the squares, you just get n. You used fractions, maybe that's a little funny. You should multiply by the squares of the denominators to get n times some very big square, but then you strip away the square anyway and you're left with n. So if you do the right algebra and this cubic curve or elliptic curve has a solution with y non-zero, you'll see that n is a congruent number. And actually, the argument works both ways. If n is a congruent number, you can do some high school algebra and find a point on this curve with rational solutions other than with y equals 0. Y equals 0 means along the x-axis. So elliptic curves have been connected to congruent numbers for a very long time. And if you prefer right triangles, you can also explain from a solution to the elliptic curve how you get a right triangle with area n. I won't do that here, but again, it's just direct algebra. But I do want to give a couple more examples and then introduce the conjecture that turns out to explain those red numbers and also explain really the black numbers, the ones that were congruent to 5, 6, or 7. So the proposition at the top of the screen is just the thing I've already said, that you can tell whether or not n is a congruent number by looking for solutions to the cubic equation with rational numbers, fractions, that's just tacitly understood, with y different from 0. And for n equal 13, 14, and 15, that's a good run of things congruent to 5, 6, and 7 mod 8, you can produce solutions using the kind of computer algebra systems that I mentioned before. My preferred solution is called is called SAGE, S-A-G-E, which incorporates Parry. It was designed by a former Berkeley graduate student, and it stood for initially software for arithmetic geometry experimentation. And that's a very powerful open source package that really does a lot of mathematical computations in mathematical research. So we know, for example, this is how we might know that 13, 14, and 15 are congruent numbers. And there is an extra proposition now that I want to bring in that uses the theory of elliptic curves, and we could kind of bring that in line with the first examples that I had when I had some, y squared equals x cubed minus x plus 1 and so on the screen. The proposition is that if there is a solution to this cubic equation with y different from 0, then there's an infinite number, that you can use that solution to generate more and more and more, like the sequence that I illustrated in one of the first slides, where the denominators are getting more and more complex. And there's a geometrical reason for that that has to do with drawing lines. So this is called the chord and tangent process. And the idea is that if you have 2 points on a cubic curve, different points, you can draw the line through them, and that line will, in general, hit the curve in a 3rd point. And the reason is that the line is just a degree 1 equation And the cubic curve is a degree 3 equation. And when you have those two simultaneous equations, they should have 3 different solutions in pairs, x comma y. And so if you have 2 solutions like this one and this one, you can draw the secant line, it's called, or chord would be a better word, and you get a third solution for your effort. And the mathematics behind it is that if the 2 points that you start with are have rational coordinates, x, y coordinates or fractions, then the third will as well. And the reason is that the coefficients of all of the equations involved are just rational numbers. So if 2 solutions are rational, the third will be rational as well. And I also said this was the chord and tangent process. If you only have 1 point, instead of drawing a chord, you can draw a tangent to that point, and then from 1 point, you get a new point that way. So this is a very well-known geometrical process that's used with elliptic curves. And in terms of fancy algebra, the word for this is that it turns the set of points into a group. A group is a mathematical object where if you have 2 things, you can combine them and get another object in the group. That's what's happening here. And since when you take 2 points, the order in which you name them doesn't change, if you change the order, you still have the same chord, or if you have only 1 point, you still have the same tangent. This is a group where the group law is commutative. Kind of P and Q give you the same point as Q and P. So the technical word for that is that it's an abelian group. And here is a little wonky slide saying that from a cubic equation, you can make an abelian group. And this group was studied about 100 years ago by L.E.J. Mordell, and he proved a fundamental theorem that if you want to describe all of the points on the curve, there might be an infinite number, you can start with only a finite number, and you can use that finite set and generate all of the points. So Mordell proved that this abelian group was finitely generated, which was a big theorem. And if you throw out the generators that don't give infinitely many points, you get the notion of the number of generators of infinite order, and that is an invariant of the elliptic curve, which is called the rank. So every elliptic curve has a rank. You can talk about the rank of an elliptic curve, and it's 0 if there are only finitely many points, and it's bigger than 0 if there are infinitely many points. The rank could be 1, 2, 3, 4, 5, and so on. And in fact, it's another open question in the whole theory of elliptic curves, whether the so on goes infinitely often. So I think the largest known rank is about 23, and people are not certain whether or not the set of all ranks will go beyond 23 or 24. Does it go on for infinity or does it stop? There are kind of like philosophical reasons in both directions. But the rank is either finite or infinite. The rank is either 0 or positive. And when it's 0, the set of solutions is finite. And when it's 1 or more, the set of solutions is infinite. And the conjecture that was given as one of the Millennium Problems by the Clay Math Institute in the year 2000, there's a $1 million bounty on this conjecture. It's called the conjecture of Birch, British mathematician Brian Birch, and Swinnerton Dyer, who's Henry Peter Francis Swinnerton Dyer. They worked together in the 1960s, and they came up with the conjecture in the case of elliptic curves. And now this is just a restatement of what I've been saying, so I'll skip over the slide. That the question of whether or not n is a congruent number is really a question about ranks. It's the question about whether the rank is positive, and the rank of what? y squared equals x cubed minus n squared x. Does that elliptic curve have positive rank or not? And this conjecture that I alluded to says a lot about that. But first, I want to explain something about something called arithmetic statistics, where you take the set of all the elliptic curves, you have a capital A and a capital B that defines the equation, and you can let these numbers grow very slowly, and you tabulate ranks. And as the thing's growing, what fraction of the ranks are 0? What fraction of the ranks are 1? What fraction of the ranks are 2? And so on. And the observation, numerical observation and kind of growing conjecture, is that as you tabulate the elliptic curves, half of the elliptic curves will have rank 0, half of them will have rank 1, and rank 2 and more occur every now and then, but not enough to have a positive percentage. So there's an infinite number, but you're dividing by the number of elliptic curves you've considered that grows bigger, so the percentage is just 0. And this is, again, one of the key open problems in elliptic curves. What can we say about ranks if we take y squared equals x cubed plus ax plus b, and we let a and b grow and do the tabulations? So there's a reigning conjecture that the rank should be 0 or 1 almost all of the time, with an occasional rank 2 or more kind of slipping in. And the higher the rank is, the less likely it is to just kind of slip in. So that's what we kind of think about ranks. And the conjecture that I want to close with is a conjecture that makes a bridge between the algebra that I've been doing and the theory of Math 1A, when you study differentiable functions in calculus. Well, to every elliptic curve, you can associate a function as in calculus. It's called the L function of the elliptic curve, and it has a value for every number, even every real number and even every complex number. We know that as a theorem only because of the work that was done by Wiles and his collaborators in proving Fermat's last theorem, by the way. But there's this L function, and there's what's called its central value, which is the value of the function at 1. And I'll explain in a second why 1 is the central value. And the conjecture, the thing that Birch and Swinert and Dyer discovered empirically around 1966, is that the rank is bigger than 0. There's an infinite number of points if and only if the L function has the value 0 at the central point 1. And this is unknown, by the way. This is already, $1 million. This is really unknown. Although what is known now, this is a theorem from around 1987, is that if the value is actually non-zero, then the rank is 0. But we don't know that if the value is 0, then the rank is positive. We know part of the conjecture. And why is this the central value? It's because there's a symmetry to this function. And if you take the argument, it's called s, and you replace it by 2 minus s, you get back either what you started with or the negative of what you started with. And whether or not you get the plus thing or the minus thing is an invariant that you can calculate very easily from the coefficients of the elliptic curve. You can let your computer algebra system, you give it A and B, and you'll say, what is the sign for this elliptic curve? And in a billionth of a second, you'll get back the answer. So here on the slide, I say it depends on the elliptic curve in a straightforward way. And the central value 1 is because if I take 2 minus 1, I get 1 back again. So if I take s equal to 1, the equation at the top of the screen tells you maybe something. If the plus sign is 1, it just tells you that L of 1 is L of 1, and you say, so what? You have no information. But if the plus or minus sign is minus, it says that L of 1 is minus L of 1, which implies that L of 1 is 0, and conjecturally, that implies that the rank is positive. And so if the plus or minus sign is negative, which happens about half the time, then the L function is 0 at the central value, and the conjecture implies that the rank is positive. And if we are dealing with an elliptic curve, y squared equals x cubed minus n squared x, it tells you that n is a congruent number. So minus sign tells you that n is a congruent number, but only conjecturally. That's the deal. And now you can guess when the minus sign is a minus sign and not a plus sign. It's when the number is congruent to 5, 6, or 7 mod 8. So I won't even call that a theorem, it's just a calculation that the plus or minus sign is negative when n is 5, 6, or 7 mod 8. And so in the table that we looked at with all the black numbers and the 3 red numbers, if those black numbers weren't there, we would have a counterexample to this famous conjecture of Birch and Swinert and Dyer, which of course we don't, because the conjecture is still there. And so we expect those numbers to appear, and they do actually appear, which is semi-reassuring. There's a mountain of evidence for this conjecture, but we go on. And now here's the thing. I explain this in these slides. If n is 1, 2, or 3, the sign is plus 1. So all we know is that L of 1 is equal to L of 1. And we have basically no information. Well, we do have some information, actually. If you look at that equation in the right way, you'll find out that the rank should be, in other words, according to the conjecture, an embellishment of the conjecture, it should be 0, 2, 4, 6, 8, and so on. It's going to be an even number. And so if you think of the philosophy that I told you involving arithmetic statistics, most of the time it's going to be 0. 100% of the time it's going to be 0, in which case n will not be a congruent number. There'll only be a finite number of solutions to the elliptic curve. But if the rank happens to squeak by and be 2, 4, or 6, for example, then n will be a congruent number. And what I tried to say before is that even if something occurs 0% of the time, it can actually occur every here and there. This is now typeset in a way that's probably more coherent than what I just told you. Namely, if the remainder is 5, 6, or 7, we expect that n will be a congruent number, and we actually find it. If the remainder is 1, 2, or 3, we kind of expect that n is unlikely to be a congruent number, but it might happen to be. And that's exactly what occurs. If we take those red numbers, 3, 34, 41, and 65, and we use our computer algebra system to calculate the ranks of the elliptic curve, these 3 red numbers are such that the rank is equal to 2, which is a positive number, and therefore n is a congruent number. The conjecture survives. So I think I say that here in a typeset way. The conjecture survives. Everything that we observe is in accordance with the conjecture. And now the question is, what can we actually prove in mathematics? Namely, if n is congruent to 5, 6, or 7, can we actually show, at least sometimes with some extra hypotheses, that n is actually a congruent number? And it turns out that there are people who've been working on this, say, for the last 10 or 15 years, and they have very good partial results with some auxiliary hypotheses. They are able to show that the conjecture is true. And one of these people, and in fact, I think three of them were all classmates in high school in Peking. And one of them was my colleague at Berkeley, Xinyi Yuan, who wrote a number of papers on the subject with some co-authors, but he's now returned and he's a professor in Peking University. So I haven't seen him in a bunch of years. And the most recent thing that I found on the web, this is a little bit troubling because I think the paper is still unpublished despite the fact that it was circulated as a preprint 8 years ago. In mathematics, by the way, this is not unheard of, but it is a little bit disquieting. The author is a very smart and interesting mathematician named Alexander Smith, and he proves that some hefty percentage of the time, if the square free number is congruent to 1, 2, or 3 mod 8, it is not a congruent number, and some bigger hefty percentage of the time, if it's congruent to 5, 6, or 7 mod 8, then it is a congruent number. And he says that these proofs complete the arguments started by these 3 high school classmates, one of whom was my colleague. Okay, so I've actually spoken for a really long time, and I think this is my last slide, and now I definitely stop.
Questions to get. Don't carry on.
Talk about his cell phones. He means his cell phone.
About the cell function, which is the central value is so important, and that there's an L function that goes with every elliptic curve. The L function, I gather, is differentiable. You said it's from, but you never showed us how to get the L function from the elliptic curve. Is that straightforward? Is that a thing that that is left as an exercise for the reader?
So the question is, so this is a question I could really answer this for quite a while. Okay, so suppose you have an elliptic curve and you want to get its L function. So the question is, what is that? So the elliptic curve is an equation, y squared equals something. And from this equation, you get a family of congruences. So you take the same equation and let's say y squared equals x cubed minus x plus 1, and you view it as a congruence mod 2, mod 3, mod 5, and so on, modulo every prime p. So this is a strange thing to do. It just means you throw out all multiples of p. But if you do that, suppose you take this thing and you view it as a congruence mod 7. Well, there are only 7 numbers, mod 7, 0, 1, 2, 3, 4, 5, 6. And so the number of solutions mod 7 in x and y is at most 49. It's a finite number. And what you can do, it turns out that the number of solutions mod p is very close to p plus 1. That's a theorem from also the 1920s or 30s. And it's traditional to write it p plus 1 minus ap. And these numbers ap, you can tabulate very simply by a computer algebra program if you input the equations of the elliptic curves. For example, you can say, what is A23 of your elliptic curve? And the output comes immediate. And the L function for the elliptic curve is defined by some infinite product over all the prime numbers, and that makes it kind of like the Riemann zeta function we were discussing before. And this infinite product is something like 1 minus AP, p to the 1 minus s, plus p to the 1 minus 2s inverse. And this is an infinite product, and the problem is that it does not converge when s equals 1. And therefore, if you ask, what is the value at 1, you can't really tell from this expression, Although in the 1960s, Birch and Swinert and Dyer found a way to figure out what it was like. Like they were able to compute it even though they really didn't know what it was. And one of the great things that happened in the 1990s, starting in 1993 and running up to 1999, is that several people, starting with Andrew Wiles, but others got involved also, actually showed that this LE of S, the LE of S is related to something called a modular form. And that was kind of the main theorem of Wiles, that elliptic curves are related to modular forms. And when you know that it's related to a modular form, then you actually can define it for all values of S, even S equal 1. And so the actual value at S equal 1 requires a big theorem from the 1990s, even though the definition of the function can be given as an infinite product for numbers to the right of S equal 1, starting with 1.5, actually. So 1 isn't even close to the edge.
Ribet equal 1 to million.
Any other questions? Ali? Yes.
So, since you've cited this paper from that's in your archive, this by Smith, well, one of the traditional things these days, sometimes at least, is not to worry too much about whether the paper is published, and then come up with your own wisdom as to whether you like the paper or you believe the paper. And if it's a paper like that, then I'd ask someone like you whether you have faith in it, whether it's published or not.
Yeah. So the question is, why do I have faith in this paper? And I do. First of all, I've heard a number of lectures by Alex Smith, and he's incredibly resourceful, and he knows the subject backwards and forwards. Secondly, he has a stream of papers. I saw one last night with some co-authors, and they're all in the subject of arithmetic statistics, and they study Selmer groups of elliptic curves and families, and he really knows his stuff. So I'm quite confident as someone distant from his work that the work is solid. But you know, and there's always this question of reliability in mathematics, which is a whole big subject that people talk about nowadays. When people work in an area, they try to find out what's known in the area, and they build on that. And then as they get more and more into the subject, they find that they have an obligation to their colleagues to really understand everything that's happened in a much deeper way than they did when they were applied standards. One thing I remember that I did when I was writing my thesis, my first research really, is I generalized work of different people, and even though I understood the work of these different people in a very passive way, in order to generalize it and prove things on my own, I had to come to understand it in a very dynamic way and really penetrate into it. I don't know if that answered your question.
Are you willing to be the spokesman for this paper?
So I will confess that I've spoken about this topic a few times before in my life. And the first time that I spoke about this topic, the paper had just been put on archive. And I did not do a quick search this time to see if there were follow-ups. But I could not find that paper published.
Okay, so did I say it go out?
To finish up, I want to ask a general question. I was wondering, how number theorist is thinking. I'm a physicist, and the way how physicists, most physicists think is that you have an object, you have image of something, and you try to understand, mechanics and properties, but you see this thing, you kind of know what it is, and you just simply try to, in many cases, just try to find mathematics that fits this behavior. In number theories, it's completely different. I wonder, how do you think?
So the question is, how do number-theorists think? And the answer, I'm sure, is different for different people, but also for me, say it's different at different times. Like if I'm thinking really theoretically, I have some object that I'm trying to probe, and it almost has some palpable identity, and it's kind of this object that I know, even though it's very abstract and I can't visualize it in any way. But one thing that has really happened since I was a student is that when I first would come to a question, like I wouldn't know, what would be true and what would be false, and I'd really have to think about it just purely abstractly and say, is this something I can prove? And if not, is this something I can find a counterexample to? It would take you a long time to figure out how things fit together. And the advent of computers has made it very easy to get some handle on what might be true. Like I remember the professors when I was a graduate student saying, Sue will have computers and we can compute the first 10,000 examples. Well, everyone can do that now on a laptop, but then if you really want to see the first 100 million examples, you can ask someone who's very good in scientific computing, and they will tell you that. And that kind of shapes the way you see things because you get a sense of what might be true and what might be false. But of course, in number theory, I do have to say that there are a lot of problems where you can probe something numerically and you don't see what's happening. There are many equations that have no solutions smaller than 18 digits or something like that. So if you just kind of search in some unsystematic way, you're not going to find them. And there's been a lot of really great number theory where people have done some theoretical work to figure out how to do a calculation and then done this very targeted calculation that came up with a concrete answer.
All right, let's thank Kenneth.